Hello everyone, welcome back to the second part of the video for circular motion for A2 physics. In the last video, we discussed about angular displacement and angular velocity, and we saw that angular displacement is basically measured in theta, that is the angle an object moves when it's moving through a circular path, and theta we measure it in radians. And then we saw what angular velocity is, which is represented by omega, and angular velocity we saw was the rate of change of angular displacement, which is theta by t. The unit for angular velocity was radians per second, right? So this is what we saw in the last class, no, the last video actually. So today we'll go into a bit more details on how to calculate angular velocity in different situations, and we will also talk about linear velocity of an object when it's moving in a circular path. All right, so let us first go for angular velocity. Now let us go for this example. Let's say we have another object moving in a circular path, and starting from point A, it's going up to point B, right? And it moves through a angle theta. And to move from A to B, it takes a time t, right? So if I want to find the angular velocity, I will write this time as theta by t, right? Omega equals to theta by t. Now the difference here is, now if the object starts from A and instead of stopping at B, it moves around the circle and comes back again to A, what does the value of theta become at that point? Theta then becomes equals to twice pi radians, right? Why? Because the object has moved a complete circle. So instead of writing theta, now we can write twice pi divided by t. And hence, and as we know, 1 by t, 1 by time period, is actually giving us frequency. We can replace this t and use the same equation to write omega equals to twice pi f. Okay, so the equation we saw in the last class was omega equals to theta by t, which is correct when the object is moving a part of the circle and the angle moved through it is theta. But when the object makes a complete circle, the angle theta is then written as twice pi, and the time period is then converted to frequency, twice pi f. So this is the formula that we will be needing a lot, because in most of our calculations or mathematical problems, we will see that the object has moved actually through a complete circle. So the frequency will be given, you have to find omega, or the time period will be given and you have to find omega. Okay, so I guess this part is clear, nothing that confusing here. All right, we come to the next part where we will see a different scenario. Now, how do we calculate the instantaneous velocity or the linear velocity of an object when it's moving in a circular path? So we have already calculated the angular velocity. The second part is the linear velocity, the velocity that we have dealt so far, that is v equals to displacement by divided by time. Now here the displacement of an object is the arc length. The displacement is the distance through which it is moving, the arc length, right? So you take a string, maybe a rope or something, okay, and you place two objects at 2 points. One object is placed at point A, the other object is placed at point C, right? So maybe you attach two stones at these 2 points and you make this string go in a circular path, just like this in the diagram. So one of the stone is attached at point C, the other stone is attached at point A, and then you rotate them. As you rotate them, when the stones move to point B and point D respectively, the one which was at C goes to D and the one which was at A goes to B, you will see that they have moved through the same angle. Both of them has moved through the angle theta, right? Now if I tell you to find the arc length, how will you find the arc length? Arc length is found using the equation s equals to r theta. This we discussed in the first video, right? Now, since from the picture it's very clear that r1 is greater than r2, we can pretty much clearly say s1 will also be greater than s2, right? So the object which was placed at A has moved a larger distance compared to the object which was placed at C. Even though they have moved the same angle, the angle moved through both of them is theta. The one which was further from the center, the object which was at O, has moved a larger distance, right? Now the next thing comes, how much time did they take? Let's say the time taken for the object to move from A to B was 2 seconds. So how much did the time pass for the object to move from C to D? this should also be 2 seconds, right? Because both of them were attached to the same string. So if A moves to point B in 2 seconds, C also moved to point D in 2 seconds, but they have different distances, right? The arc length is not the same. So as we can see, S1 is larger and S2 is smaller, but even though the distance was larger, it took the same time. It took 2 seconds to go from A to B, and it took 2 seconds to move from C to D. Now here comes the question. If they have different distances, if A to B is larger in distance than C to D, how did they cover the same distance? How did they cover different distances in the same time period, right? So here is what we have to learn from here. Okay, so let us now see how does that happen. So what was the formula for finding the velocity, linear velocity? It was displacement divided by time. So if I want to find the velocity of the object which was at A, the displacement would be S1 divided by the time taken, and the object which was placed at C, if I want its velocity, I will write S2 divided by T. Now we are saying that they have moved the same, they have moved the distance in the same time period, so the T is same for both of them. Now S1 is larger than S2, right? S1 is greater than S2. Why? Because R1 is greater than R2. So if S1 is larger than S2, we obviously know the object which was moving from A to B has a larger velocity. It has to have a larger velocity so that it can cover a larger distance in the same time period, or else it's not possible for an object to cover a larger distance in the same time period as an object which is covering a smaller distance, right? Only it is possible if this object is moving faster, and from our equation we can see that the object is actually moving faster since S1 is larger than S2. So this is what you have to remember, that an object moving in a circular path along the same angle, that is theta, will have different linear velocity even though their angular velocity might remain the same. If I want to find the angular velocity of the object which was placed at A, omega equals to theta by T. Okay, if I want to find the angular velocity of object placed at C, it's again omega equals to theta by T, because they have moved through the same angle. The object at C and the object at A has moved through the same angle theta, so theta is same. They took the same time to cover the distance, so T is also same. So we can say the object at A and the object at C had the same angular velocity, but do they have the same linear velocity? No, they don't have the same linear velocity. They have different linear velocities but same angular velocity. So how do we calculate linear velocity using this equations? So velocity equals to displacement divided by time. Now here the displacement is the arc length, right? So S equals to R into theta divided by T, or we can write R into theta by T. Again, what we learned a few minutes back, theta by T is actually omega, right? Omega equals to theta by T. So we can replace this theta by T as omega. Since omega is same for both of them, omega is constant, we can very easily say the linear velocity of an object moving in a circular path depends on the radius, or how far the object is from the center. So the further the object goes from the center, the larger the radius, the faster will the object travel. Its linear velocity will be larger. Why? Because its arc length will be larger and it has to cover the larger length in the same time period, right? So if it's moving through the same angle theta, but it's covering a larger distance, then it has to move faster, and we can show it from the equation by using this equation, v equals to r omega. So if you're told to find the linear velocity of an object moving in a circular path, this is the equation that we use. Okay, so we basically discussed about two equations here. One of them is v equals to r omega, and the other one was omega equals to 2 pi f. Okay, so we'll keep it up to here in this video, and in the next video we will discuss more about this topic. Okay, all right, thank you everyone.